Hi everyone and welcome to today's video on power functions. It's weird really because I think of power and then I've got like either batteries, that's not particularly funky, or He-Man. Now that's a throwback to my younger life and it's playing behind me and wow, He-Man and the power of, I'm sure he said Thor. I don't really know now. It's weird because that was like many years ago. I think they did a reboot. And then you go Mighty Morphin Power Rangers. Power Rangers, yeah, again. I must have led a very deprived childhood because I don't remember watching these either. So what has this got to do with anything to do with maths? Absolutely nothing. But it was an interesting way to open a video. Bye bye. So welcome, thank you very much for joining me. If this is the first time, do me a favor, can you click the little subscribe button over in that corner if you're watching on YouTube, and if not, well, just head over to YouTube and watch my videos. It's really good to see you. MaffsGuru, trying to do what I can to sort of educate everyone out there in the world, and all the subscribers in the world will make things awesome for me. Anyway, what's today's lesson about? Power functions. What is meant by a function? Now, actually, if you read the stuff that's being highlighted above, you'll see that there's a lot of terminology. And the thing about methods is it's all terminology. So basically, in this chapter, we've been looking at range of functions. Now, the strange thing is there are lots of them. And many of them you have to know almost intimately, and that's something I'm not really getting into because that's way embarrassing. But the point of it is, you've got to understand what a square root graph looks like, what a hyperbola looks like, a truncus, and all these sorts of graphs, which we are coming to, I promise. With regards to language, this video is just going to briefly go over bits and pieces. And I suppose the first one is this strictly increasing and decreasing. The thing about methods is it's all this notation stuff. And a lot of the questions, particularly in the exam, throw people because of the notation they use. The maths, I promise you, is actually not that complex. Algebra, yes, that's complex. If your algebra skills are good, you've got a fair chance of doing well. But in this situation, if you read that notation, it says if x2 is greater than x1, then the function of x2 must be less than the function of x1. This function is strictly decreasing. So what they're basically saying is, if I choose two x values and call it, say there's my x1, and there is, I don't know, my value of x2, then what it says is, if the function of x2, that means if the y value for x2 is less than the y value of x1, the function is strictly decreasing. Now, I don't know about you, not exactly brain science, is it, or rocket science. The point of it is, though, we have to know the terminology. So what about strictly increasing? Well, it just does it the other way around. If x2 is greater than x1, and then function of x2 is greater than function of x1, it's a strictly increasing. So again, if x2, so let's choose my x2 value here, is greater than x1, let's choose my x1 value there, is the function of x2, i.e. is the y value of x2 greater than the y value of x1, it is strictly increasing. Again, not particularly challenging. Now, one of the things you do need to know is power functions. And I don't think I can do that for the whole video, but we'll give it a go. Now, power functions are basically anything to a power, any graph to the power. So y equals x to the power of 2, y is equal to x to the power of 3, y is equals x to the power of 4. These are power functions, and many of these you need to know what they look like, the general shape of the graph and important key points. Okay, so when we have positive integers, and obviously an integer is a whole number, and as we can see 2, 3 and 4 are all positive, these are the graphs you're going to end up with. Now this one here is y equals x squared. The blue one is y equals x cubed. And the green one is y equals x to the power of 4. Now, if we were to take out that graph of y equals x cubed, you notice the y equals x squared is fairly wide. Y equals x to the power of 4 sort of narrows in, and be very careful with this word narrows. What we say is dilate closer to the y-axis, or is closer to the y-axis, all sorts of language coming up in that as well. And the y equals x cubed, which is that great graph that does that, that's beautiful as well. Now they're all positive integers. Let's sort of narrow that down to positive odd powers. And you can see here, by the way, I use desmos.com for this. They are not sponsoring these videos, thankfully and unfortunately. I just think it's a great piece of software. And it's free and it's online. Desmos.com. I could make that into a jingle. But the point of it here, what we notice is when we have positive odd powers, so we've got a power of 3, a power of 5, and a power of 7, Lo and behold, the graphs all have the same or similar attributes. They have the same shape, absolutely. And every single one of them goes through 0, 0. What we tend to notice is, though, that the bottom section, so when we have y equals x cubed, this sort of leveled out bit, if you want to use a really unmathematical term, is relatively short. But as we get y equals x to the power of 5, y equals x to the power of 7, that seems to become longer. And the sections of the graph that go up and down go up with a far steeper gradient. So that's important to know. But as I've listed here, we've got things called odd functions. Now, if you remember what an odd function is, that's when you put f to the minus of x is equal to minus of f of x. Otherwise known that there's been a rotation of 180 degrees around the origin. Okay, so that's an odd function. It's strictly increasing. As we said before, if I choose x values getting higher and higher on my x-axis, the y values for each of those x values gets higher and higher and higher. It's a one-to-one function. We'll come back to that in a bit, but long story short, if I draw a horizontal line through it at any point in that graph, it'll only cross once. And there are some key points, 0, 0, 1, 1, and minus 1, 1. Now, again, when we sketch these things for methods, you have to put coordinate values down. I haven't put on these graphs because I'm just showing you the general idea of what they look like. But later on, you have to label all sorts of points. What about positive even numbers? Well, here we go. Wonderful. Well, we already know this graph here. Again, we would suggest we are intimately acquainted with it. And my mind is just going off on tangents I don't even need to think about. But again, if we now compare y equals x squared, y equals x to the power of 4, and y equals x to the power of 6, they all have very similar shapes. The y equals x squared, which is the red line, is fairly wide. Well, it is in comparison to there. But what we notice again is as we get to x to the power of 4 and x to the power of 6, that bottom part of my graph starts to level out. So x to the power of 4 is quite level, x to the power of 6 more level. And again, it's seemingly bending in closer to my y-axis and getting steeper, faster with each of those. And that sort of makes sense. If I'm going to put a number to the power of 6 and I'm multiplying it by itself 6 times, it's going to zip up fairly quickly. So what are the important functions from here? Well, as I can say here, it's an even function. Now what that means is that if I put f to the minus of x, it should come out as f of x. So if I replace x with a minus x, it should come back to my original function. Alternatively, it's a reflection. It's a graph that it is symmetrical around the y-axis. Okay, so again, that's another sort of trick there. Key points again, 0, 0, 1, 1, 1 minus 1, 1. And it's strictly increasing and strictly decreasing for various parts of those graphs. And obviously, you know, if we look here, it says strictly increasing for all x values greater than 0. You're going to have to remember these. Tattoo them somewhere. Don't tattoo them somewhere. Please, God, don't tattoo them anywhere. What about negative odd integers or odd negative integers? Again, same idea. We know what the graph of y equals x to the power of negative 1 is. Now, we don't normally write it that way. We would normally write it as y is equal to 1 on x. And we know what that looks like. That's a hyperbola. That's the graph that does this and this. And very much so, if we look at the red graph here on my x's, I notice very much that, yes, there is my typical hyperbola. But then we get y equals x to the minus 3. Now that's the same as 1 over x cubed. That's my blue graph. Now again, what we notice is that it has that same shape, but it seems to be getting faster, much quicker for smaller values of x, and then bottoming out and getting closer and closer much sooner. Likewise with x to the power of negative 5. So knowing the general shape is really helpful to me. Now, if we look at this section here, we know that there's sort of 4 key pieces of information. One is an odd function. And what does an odd function mean? Well, it means it's rotated around the origin 180 degrees, a horizontal asymptote and a vertical asymptote. Now, there are 2 lines on this graph in which none of these functions will ever meet or cross, and that's an asymptote. Now, if we look at the idea of y is equal to 1 on x, and this works with absolutely any of those functions there, we know that one value x can't be is 0. We cannot divide by 0 because we get an undefined value. So we now know that x cannot equal 0. Well, if x can't equal 0, that means that this line here, the line x equals 0, otherwise known as the y-axis, must be an asymptote. But what about the other way around? If I rearrange this equation and have x is equal to 1 on y, then we also see that y can't be 0 as well, because 1 divided by 0 can't happen. And the line y equals 0. So y cannot equal 0. And so the line y equals 0 happens to be the x-axis as well. So there are those two asymptotes and the reasons why. All right, the maximal domain of that is basically all real values except x equals 0 and y equals 0. What about even negative integers? Well, once again, we have y equals x to the power of minus 2. Well, we know what that means. We know that that's the same as y is equal to 1 over x squared. And we get to our truncus. And again, I have elephants going through my head. And I know that Dumbo is about to be released at cinemas. And now I'm doing plugs for Disney. Anyway, moving on. Same point there. If you think about this now, well, can we have an x value of 0? No. Can I have a y value of 0? No. And so we now know that we have horizontal and vertical asymptote. It's an even function because it's reflected in the y-axis, and it has a maximal domain of all values except x equals 0, all real values except x equals 0. But once again, remember that there are key points on this graph, and you'll notice that they all go through negative 1, 1 and 1, 1. And they have the same shape, that continual, that sort of volcano-like shape, if you will. And my fingers just went missing off the screen. Wow, freaky. Fractional indices, well, this is the last part of this video, and they are incredibly important. These particular graphs, much more than I would like to admit, particularly the graph of y equals x to the power of half. Now, please, please, please note that y is equal to the x to the power of half is exactly the same as the square root of x. And the graph of the square root of x is used ever such a lot, all right? I can't tell you how much. And so looking at this graph here, or function here, we know that the red graph is that root of x. It starts at 0, 0. It includes 0 as my x value. So my domain is basically given by 0. Oops. So my domain is given from 0 to infinity. My range is given by 0 to infinity. And then we have this y equals x to the power of 1 cubed. Now, it's not formally taught, I don't believe, in methods 3 and 4, but I'm telling you now, it's really, really useful to know what y equals x to the power of 1/3 looks like. And throwing it in there, and for your own sort of curiosity, have a look up, load up desmos.com, put in that graph y equals x to the power of 1/4 and see what happens. Okay, I think you'll be very, very interested. These graphs are going to be the staple of this whole course. I cannot tell you how important this is. There's no examples for me to go through because the whole course is based on graph drawing, graph sketching, and knowing how these graphs look. Later on, we're going to come to a chapter called transformations, and I'm telling you now, all you're going to be doing is moving these graphs horizontally, vertically. You'll be stretching them, you'll be stretching them, you'll be rotating them. If you don't know what they look like and you don't know where their key points are, you're going to find it very, very difficult. So please, please, please go back and watch the video again and sort of learn what these graphs are. Right, I am done. As usual, it is fabulous having you watching these videos. Thank you very much. One of the shortest ones for a while because there was nothing really much going on. If you haven't already done so, please, 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 and you're watching on YouTube, do me a favor and subscribe by clicking that large circle. Every subscriber makes me know that actually I'm doing this for a reason. So greatly, greatly appreciate it if you could not only subscribe, but tell your friends to click on over and subscribe as well. Otherwise, it's good seeing you. There's a new video loading for you over there. This is MaffsGuru, out.